Hi, this is Mrs. Villette, and this is a video for Unit 4 of AP Calculus AB, and this is an introduction to the relationship between derivatives and motion. So we're talking specifically about straight line motion here. So, for example, a car driving along a straight road or a person walking along a straight path. And I realize that a lot of you have had physics, so some of this will seem like it's review. What we're going to try to do is tie the understanding that you might have from a physics class into calculus. So we need to start with some definitions. Our first definition is our position function. We are usually going to call it s of t or x of t. This is usually for an object that's moving along the x-axis. And this is going to be the position of an object as a function of time, lowercase t. We want to make sure that in applied problems we have units on our position and we have units on our time. So for example, meters and then seconds. Displacement over an interval a to b, so this is a time interval, is just the change in position. So you would take your position at the end of the interval, which you would call s of b, and you would subtract your position at the beginning of the interval s of a. So this is just basically the change in the outputs of the function. Average velocity is the displacement, so the total distance traveled divided by the elapsed time. So average velocity would just be the change in position, s of b subtract s of a, all over b subtract a. This is essentially just a slope calculation, so change in output divided by change of input. Velocity or instantaneous velocity is something slightly different. The first thing is from a physics perspective, velocity is actually a vector. Vectors have both magnitude, in this case the magnitude of velocity is the speed, and direction. For our purposes for straight line motion, the direction is going to be left-right or up and down. In single variable calculus, we're just going to treat velocity as if it's a number that represents the instantaneous change of position. So it'll essentially be the speed, but with a sign to indicate whether the function is moving left versus right. Using derivatives, velocity is just the instantaneous rate of change of position, and so that would be the derivative of the position function, so it would be s prime of t. Now, acceleration is the change in velocity, the instantaneous rate of change of velocity. So acceleration is the first derivative of velocity, so v prime of t, which in turn makes it the second derivative of position. Now, something to keep in mind both from a physics perspective and also for multivariable calculus is that acceleration, like velocity, is also a vector, so it has magnitude and direction. For us, the sign of the acceleration depends on the slope of the tangent line to the velocity. So if your velocity is increasing, so your velocity function has a positive slope, we will call that positive acceleration. And if your velocity is decreasing, we will call that negative acceleration. Okay, so let's take a look at an example. We have this graph in figure 1, and this is a position graph. So this graph is telling me the position as a function of time. We have an object moving in a straight line. If we have positive velocities, we're going to interpret that as the object moving to the right, and a negative velocity would mean the object is moving to the left. And at each of these points indicated, we are going to determine whether the velocity and acceleration are positive, negative, and 0. So keep in mind this is the position function. So this point A is just our starting position. So this is where we start. Now I can see that as I move to the right, my position is decreasing. I can also see that if I draw a tangent line at point A, that tangent line has negative slope. That means my velocity at point A is negative. Let's go ahead and just go through all the velocities first. So at point B, if I draw my tangent line, that tangent line clearly has a slope of 0. So the velocity here is the slope of the tangent line. We're just measuring sine right now. At point C, my tangent line is positive sloped. So we're going to say at point C, my velocity is positive. At point D, it's negative. At point E, it's negative. And at point F, it is positive. Okay, the acceleration is a bit trickier. So for the acceleration, I have to look at whether the velocity is increasing or decreasing. So if I look at point A, I'm going to look at a point slightly before point A and a point slightly after point A. I see that my velocity is negative near A, but my velocity is becoming less of a negative number. So let's say that I assigned this a slope of -5, and I assigned this a slope of -4. Those aren't the actual numbers. This is just to kind of get our head wrapped around what's going on here. Well, if I look at those numbers on a number line, here's -5, here's -4, I'm going this way. So even though my speed is getting slower, my velocity is actually increasing. My velocity is going from -5 to -4, and that is an increase of, in this made-up example, 1 unit. So that means I actually have positive acceleration. All right, let's look at B. So if I look to the left of B, I have a negative velocity. At B, I have a 0 velocity, and at C, I have a positive velocity. That again is following the same trend of an increasing velocity. So I go from negative to 0 to positive. My velocity is increasing, which means my acceleration is positive. Okay, part C is a little bit tricky, so we may need to zoom in here to get a better idea. So in part C, it looks like we're really, really close to the inflection point. And without a graph of the velocity, I can't see exactly where the inflection point is, but I think the inflection point is about right here. So if I look slightly to the left and slightly to the right of C, I think my trend is that as I go from left to right, my velocity, which is now positive, is increasing. So I'm going to say my acceleration is positive. Now don't worry if these guesses feel a little bit fuzzy. On the next page, we're actually going to see the velocity graph and be able to definitively answer whether acceleration is positive or negative. Okay, at D, my velocity is negative, but if I look slightly to the left at a tangent line versus slightly to the right, it looks like my tangent lines are getting steeper. So again, if I assign this a number, like let's say this one's -4 and this one is -5, I can now see that instead I am starting at a velocity of -4 and going toward a steeper negative, so going from -4 to -5, which means my velocity is decreasing, so that means I have negative acceleration. Okay, at E, we need to do the same basic thing. I think E may actually be the inflection point. What we need to do is zoom in, and if the function looks like that is the place where it has the steepest slope and it's sort of the straightest, we have found the inflection point, and the inflection point is where this function changes from concave down to concave up. At that inflection point, my acceleration should be 0. So on the left, my velocities are decreasing, but on the right, my velocities are increasing. And right at that middle is that place where the velocity, the change in velocity, not the velocity itself, is 0. So my acceleration is 0. And again, we'll be able to confirm this on the next page. So here my acceleration is 0. Okay, I have one point left to talk about, which is point F, and I want to look slightly to the left and slightly to the right. So I have a steep positive slope. It's really hard to actually see this, but I actually have an even steeper slope as I move to the right. So that means my velocities are increasing and my acceleration is positive. So go ahead and look at the next page and we will be able to check our work. So in example 2, we have the same position function, which is our solid red graph from example 1, and we now have the velocity graph, which is the green dashed graph. So what we need to do is verify our answers from example 1. So you might be wondering how this additional velocity information can help me confirm my answers. We're going to take a look at a few things now that we have the velocity graph. For the velocity graph, we can think of velocity either as the slope of the tangent line to s of t, or we can think of it as the y-coordinate of the velocity graph v of t. So our v of t is this dashed line. So we've already thought of it as the slope of the tangent line. When we're verifying our answers, we're going to think of the second option, the y-coordinate of the velocity graph. So if I look at point A, for each of these points, I'm going to go ahead and drop anchors, which means I'm just going to trace them down to the x-axis, and then I'm going to line those up with the corresponding points on the velocity graph. So I'm drawing a perpendicular Now I want you to notice that point C is slightly to the left of the maximum. It's actually pretty hard to tell the maximum velocity. And point E, it should, if I've designed it correctly, be right on that minimum velocity. So point E is what we call an inflection point, but point C is just slightly to the left of it. Okay, so at point A, clearly the y-coordinate of my velocity is negative, which corresponds with what I have up here. And I actually think I have drawn point B incorrectly. I didn't quite do a perpendicular. It should go straight down and hit on that x-intercept. Okay, so fixing that, point B, the velocity, the y-coordinate of the velocity is 0. Point C, the velocity is positive. Again, I'm just looking at the y-coordinate, whether it's above or below. Point D, my velocity graph is negative. Point E, my velocity graph is negative, and point F, I didn't finish. Point F, clearly my velocity, the y-coordinate is positive. So we're not using tangent lines anymore, we're just using the actual graph. Now for our acceleration graph, we are going to look at the slopes of the velocity graph. So acceleration is the derivative of velocity, so if I want to know whether the acceleration is positive, negative, or 0, I need to know whether my tangent line has positive, negative, or 0 slope. So at point A, pretty clearly, we have positive slope. I'm going to go ahead and go through and just draw my little tangent lines real quick. Point C, as I said, is just slightly to the left of that inflection point, whereas D is right on it. So going through, point A, we have positive slope to the velocity, so positive acceleration. Point B, positive slope to velocity, positive acceleration. Point C, getting pretty close to 0, but still positive. Point D, I forgot that one. Point D, we have negative slope of my tangent line, so I have a negative acceleration. Point E, this should actually be 0. I think I may have copied it wrong. And then at point F, clearly the slope of my tangent line is positive, and that lines up with that. So the next thing that we're asked to do is draw the acceleration graph. So the acceleration graph should be the derivative of my velocity graph. So I'm looking at my velocity graph, and I'm going to first determine where my velocity is 0, and those are going to become the x-intercepts of my acceleration graph. Then I'm going to look at the velocity graph. Wherever the velocity graph is increasing, its derivative should be positive. So I'm going to start out with a positive derivative. Anywhere where the velocity graph is decreasing, so from here to point E, my derivative should be negative. And then anywhere the velocity graph is increasing, my derivative should be positive. Now you may notice that I've drawn the acceleration graph as a parabola. That is justified because it appears that my velocity graph is third degree. So it might be like something t cubed plus something t squared plus something t plus d. So if I were to take its derivative, that would be 3a t squared plus 2b t plus c, which is quadratic. So my acceleration graph appears to be second degree, whereas my original graph, my original position graph, appears to be fourth degree. So keeping in mind that the order goes position, and then its derivative is velocity, and then its derivative is acceleration, it makes sense that if we started with a degree 4, then we would move down to a degree 3 in my first derivative, and then I would move down to a degree 2 in my second derivative. And if I kept going, the derivative of acceleration would be jerk, and that would be first degree or linear. Okay, now to answer the last question, when does the object change directions and how do you know? So the object changes directions anywhere you have reached a minimum or a maximum on the graph. So obviously at point B, at this other point that we haven't labeled, and then there's one more place. These are also the places where your velocity changes negative to positive or vice versa. So the direction changes happen at point B, and then we'll go ahead and add some labels to those other points. So I've called those other 2 points P and Q. So for part C, we can say that the object changes direction at points B, P, and Q, and the reason we know is that the velocity changes sign. So we can look at the velocity graph and we can say, okay, to the left of point B, my velocity was negative, and then it went 0, and then it went positive. It's very important that you actually observe that sign change in the velocity, not just a 0 velocity. So just one little quick add-on that I wanted to share with you is if we have a function that does something like this, for example, we would have a place where we would have velocity of 0, but we wouldn't have a change in direction. So just having a velocity of 0, so if this is my position function, then having a velocity that's 0 at a particular point doesn't guarantee you a change in direction. It just says that your object is instantaneously not moving at that place.